Okay, so today we're going to continue talking about apportionment. Just wanted to recap for you guys that tomorrow is actually going to be a review day, so if you have any questions on today's lesson or any questions from last night's homework, we can talk about any of those tomorrow. Wednesday we have the early dismissal, but then Thursday you guys will have a quiz just over apportionment. Alright, so today our goal is to talk about Webster and Hill methods. So we're going to continue on with the exact same example that we had used before. We have Central High School and we're talking about the sophomores, juniors, and senior classes. So we still have 20 seats that we are working with. Okay, so always make sure you guys know how many seats we have. Alright, so we always start out every problem the exact same way. We find the ideal ratio. So remember, the ideal ratio just means that we add up the total populations of each of the classes. So we would just add together the 464, 240, 196, and then we would divide them by the number of seats, which we said was 20. Okay, so we calculated this on Friday, and we found out that they had 45 total. So this meant that one seat on student council was representing 45 students of their class. Alright, so what we need to do from here is talk about what they call the adjusted ratio. So if you guys remember, we talked about adjusted ratio with the other method as well. So here is the formula. And we have class size divided by the initial plus 0.5. And we actually have another piece, which is class size divided by initial minus 0.5. Okay, so when we talked about the two methods on Friday, we always had less seats than necessary. So we were either 1 short, 2 short, or 3 short from the total that we needed. So a lot of times we were adding them up and we had like 19 seats instead of the 20 that we needed. Well, with Webster and actually Hill as well, which is going to be the second method we talk about today, we can actually have too many seats, meaning we have to take away 1, 2, or 3 from somebody. Alright, so in a second I'll kind of talk about how we use these and how it is different to have the plus 0.5 or minus 0.5. So let's kind of continue on here. Alright, so just like before, quota works the exact same way. So once you guys have calculated your ideal ratio, the quota is always the class size divided by that ideal ratio. And you guys will notice that these quota values are the exact same from what we talked about on Friday. So for example, my class size here is 464. If I divide it by 45, which is my ideal ratio, that gives me 1031. And since you guys took this down in your notes on Friday, you guys can probably just write the 1031. And then for this one, we'd take 240 divided by 45, and we get 5.33. And then we get this 196, and divided by 45, and we get 4.36. Okay, so that is the exact same that we did on Friday. But remember what we talked about on Friday was we can't actually have these decimal values. It doesn't make sense to have 10.31 of a person sitting on this class board. So what do we do? Well, before we were truncating, and the Webster method that we're going to talk about today, the initial apportionment is actually done by rounding. So if it's 0.5 or higher, you guys would round up. If it's less than 0.5, then you round down. So just rounding like you guys have always known it. So if we take a look here, over here my decimal value is 0.31. Okay, well 0.31 is less than 0.5, so we would round down. And you guys are rounding down then to the nearest whole number, so that would be 10. My next one is 0.33. So if you look here, 0.33, we would also want to round down, so that would round down to 5, the nearest whole number. And this last one here is 0.36, which is also less than 0.5, so we'd also round that down, so I go down to 4. Okay? Alright, so we always want to make sure that we do a count at this point. This is 19. Now remember, we had 20 total seats, so we are 1 short, meaning I have to add 1 seat to somebody's. Alright, so Webster method says we then do the adjusted ratio. So that's these two formulas from above. So it's either class size, and then that's divided by the initial plus or minus 0.5. And this is what you guys will see on the formula sheet that you guys will get for the quiz. So you will need to know whether or not you are adding 0.5 or subtracting 0.5. So because I down here said I need to add 1 seat, that means that we specifically in this case are going to be using the addition of 0.5. If I was 1 too many, like I had 21 seats down here, then we would do be doing minus the 0.5. Okay, so we need a seat, so we add 0.5. All right, so let's talk about what this would be. So class size is 464 divided by the initial plus 0.5. So if I take 10 and I add 0.5, so that would be 10.5. Okay, so you guys could just type that into your calculator and you would get 44.19. And again, guys, please make sure that you are typing these in and double checking that you are rounding correctly. All right, the next one, my class size is 240, and I'm going to divide it by the initial, which is 5 plus 0.5. So it'll be 240 divided by 5.5. Okay, so again, you guys could type that into your calculator. We get 43.64. All right, and this last one here, we get 196 divided by 4 plus 0.5, or 4.5. All right, so that's 43.56. All right, now we always deal with the adjusted ratio the exact same way. Okay, closest to the ideal ratio will gain the seat. Now, if we were subtracting 0.5, it would work the same way as well. The closest to ideal ratio would just lose the seat. So it's always in relation to the ideal ratio. So remember, from above here, our ideal ratio that we had was 45. So we are looking for the one that's closest to 45 here, which is this top one. All right, so they gain the seat, so they go to 11, and the other ones here would stay the same. Okay, so Webster method, you round just like normal rounding. Okay, and then from here, do your count. If you need to add seats or take away seats, you'll do the adjusted ratio. And then those values, you look to see which one is closest to your ideal ratio to either gain or lose the seat. All right, let's talk about the Hill method. Now, something we need to talk about before we actually do the Hill method is something called the geometric mean. So the geometric mean of two numbers, x and y, so this could be any two numbers, is the square root of their product. So we would just multiply them together and then take the square root. So we are actually going to use the geometric mean as a comparison. So instead of rounding like we did in the last example, we now will get this value, the geometric mean of two values, and then we are going to make a comparison. All right, the adjusted ratio for the Hill method looks insane. It looks crazy, but it's actually not that bad once we actually go through an example here. So we will take the class size and we will divide it by the square root. We'll have the initial apportionment multiplied by the initial apportionment plus 1. Okay, now if we need to take away a seat, because the same thing can happen like we just did with the last one, it's going to be the exact same thing as this, except for we can also have this initial minus 1. So always the initial multiplied by either initial plus or minus 1. Okay. All right, now I'm just going to kind of click through these quickly because we already know how to calculate the quota, class size divided by ideal ratio, and notice the values are the same. All right, so before we start anything, guys, we always have to calculate this geometric mean. So geometric mean is just the square root of the product of two values. Okay, so how do we determine what two values we actually use for the geometric mean? So for example, for this first one here, if I have 10.31, you guys can kind of think about this. I'm going to write this up here. Think about a number line. I know if I have 10.31, that lies between 10 and 11. So basically you guys are thinking about the two integer values that are either below and above the value that you have. So we actually will use these two values, 10 and 11, then for the geometric mean of this one. Okay, so we'll use 10 and 11. It should always be consecutive integer values. All right, so again, you guys could type this in your calculator, and we would get 10.49 if you round correctly there. All right, now if we do the same thing with this one, so think about 5.33. Okay, so if I have 5.33, that would lie between integers 5 and 6. So we would be using 5 and 6 then for the geometric mean here. So square root of 5 times 6 would give us 5.48. Okay, and then the last one here, 4.36. Well, we know that 4.36 lies between the integer values of 4 and 5. So square root of 4 and 5 would give me 4.47. Okay, so once we have all these geometric mean values, we can now start to make a comparison. And basically what we're doing is we are comparing the quota with this geometric mean. So the way that this works is that if my quota, so here are all my quota values over here, if it is less than the geometric mean, then we round down. Okay, so if my quota, if this value over here is less than the value in the middle here, my geometric mean, then we round down. But if the quota is bigger than the geometric mean, we would round up. So if this value over here is larger than the value over here, we would round up. Alright, so let's compare the first one. So this first one here, we have 10.31 and we've got 10.49. So 10.49 is greater. Okay, so if you guys look here, it says that my quota is less than my geometric mean, so we would need to round down. Okay, now we round down to the lower value here, so it's going to be one of these two. So if we're rounding down, we'll round down to this lowest one. If we were rounding up, we would have rounded up to 11. Alright, so again, let's talk about 5.33. That is less than 5.48. So again, the quota is less than the geometric mean. So if I look back over here, between 5 and 6, my lower one, if I'm rounding down, would be 5. And the last one here, I have 4.36 and 4.47. So again, my quota is less than my geometric mean. And so I would round this down to 4. Alright, so from here, add these up, we get 19. Alright, so again, we're in the same boat. We need to add a seat. So in terms of the adjusted ratio, it's this formula that we had talked about up here. So class size divided by square root of initial multiplied by initial plus or minus 1. And it works the same way. If you need to add a seat, which we do, we are only at 19, we need to get to 20 seats. So we are adding a seat, so we would be adding the plus 1 here. Okay, if we had too many seats, like 20, 21, okay, then we would be subtracting. Alright, so let's go ahead and calculate the first one. So we always take our class size, so 464, divided by the initial. So initial would be 10 times, we're doing initial plus 1. So initial plus 1 would be 11. So we're going to have 10 times 11, and then we're going to take the square root of that value. Okay, so that would give us 44.24. Alright, next we have 240. And we are going to divide that by initial, which is 5, times initial plus 1, so that would be 6. So we're going to have 5 times 6, and then we're going to take the square root of that value. Okay, so that's 43.82. Alright, and the last one, we have 196, and we're going to divide it by the initial, which is 4 times 4 plus 1, which would be 5. So 196 divided by square root of 4 times 5, which would give us 43.83. Okay, once you guys have your adjusted ratios, it is always a comparison then to the ideal ratio, and if you remember, ideal ratio for us is 45. So if we look down here, closest to 45 is this top one here, so they would gain the 1 seat. Okay. Okay, so again, this final apportionment is always the same. Okay, always the closest one here to the ideal ratio gets the seat. Okay, or closest one here would lose the seat. Okay, so this is doing the same examples that we had done the other day with each of the methods. So let's actually try a new example here to make sure that we understand both methods. Alright, so we have City College is made up of 5 different departments. We've got communications, accounting, marketing, psychology, and technology. So we've got a total of 120 teaching positions are to be apportioned based on the school's enrollment. Alright, so basically guys, here are my class sizes. So we basically have 5 classes, and we need to apportion. We have 120 teaching positions. So this is what we are splitting up. So first of all, if we were to find the total enrollment, so if we were to add together these 5 classes and their enrollment, that would give us a total of 4,950. Alright, so the ideal ratio is always our total population divided by the number of seats. Okay, so total population was 4,950, and we have 120 teaching positions that we are splitting amongst them. Okay, so that means 41.25. So this means one teaching position per every 41.25 students. Okay. Alright. So this question here, what does that mean in this problem? So that's what this means. Okay, you guys should know and understand what ideal ratio means. Alright, so next let's talk about our initial quotas. Okay, so in order to get the initial quota, we always use this ideal ratio, so 41.25. So we take our class size and divide it by 41.25. So that's what we're going to do for each one of these. So class size here, 2,425 divided by 41.25. Okay, so that should give us 58.79. And next one, we'll take class size 745 and divide it by ideal ratio 41.25. Okay, so that gets us 18.06. And after you guys have written down, a couple examples of what these fractions are, don't feel like you have to write down every single one of them. Okay, so marketing would be 497 divided by 41.25. And then psychology would be 230 divided by 41.25. So 5.58. And technology, 1053 divided by 41.25. Alright, so 25.53. Alright, so again, none of these values actually make sense in the real life because I can't have 58.79 teachers teaching communications. That doesn't make sense. I have to have a whole number value here. And that's why we have these different methods. There are different ways of splitting up these decimals that we get. Alright, so remember, Webster initial says that we round. Okay, so we are going to round these values just like normal. So you guys are looking at the decimal value. So if you guys look at this first decimal value over here, we have this 0.79. Well, 0.7 is higher than 0.5. So this is going to round up to 59. Okay, 0.06, that is below 0.5. So this will round down to 18. 0.05 is less than 0.5. So it will round down to 12. 0.58 is bigger than 0.5, so this rounds up to 6. And 0.53 is bigger than 0.5, so it also rounds up, so this will be 26. Okay. Now, from here, if we take a second, if you guys added these up, and this is something that you guys again could just basically type straight into your calculator. Okay, so if we add these up, we end up with 121. Okay, now remember, we only had 120 teachers that we could apportion, so right now we actually need to subtract one seat. Alright, so let's talk about the Webster adjusted ratio. So Webster adjusted ratio says that we will take over here our class size. We're going to divide it by the initial plus or minus 0.5. Because I need to subtract a seat, we are going to do initial minus 0.5. So my class size divided by initial, 59, minus 0.5. So 58.5. Okay, so that gives us 41.45. Okay, and then over here we'll have 745 divided by the initial 18 minus 0.5. So if I subtract 0.5, that's 17.5. Okay, so it gets me 42.57. And we'll take marketing, 497 divided by the initial 12 minus 0.5, so that'd be 11.5. So that's 43.22. And then we have psychology, 230 divided by the initial 6 minus 0.5, so it'd be 5.5. So that's 41.82. And then we've got technology, which is 1053 divided by, this will be 25.5. Okay, now we are only looking to take one seat away. Now remember, up here, let's look at our ideal ratio. Remember, 41.25. So if it is 41.25, I'm looking for the very closest to 41.25. Which, if you look at this last one here, here's 41, but this one's 41.29, so this is as close as it gets. So right here, so they will actually drop the seat. So they went from 26 to 25, and everybody else will remain the same. Okay, so closest here to the ideal ratio loses a seat. And again, if you guys had -2 here, you had too many seats, it would be the two that are closest that would both lose a seat. Alright, let's talk about Hill method. So geometric mean is a square root of two values. So remember, we always want to look at the quota. So here's my quota, 58.79. So 58.79 lies between two integer values, 58 and 59. So those are the values that we use. And again, you guys could just type that straight into your calculator. You would get 58.5. And next we have 18.06, and 18.06 lies between 18 and 19. So that's the two values that we'll use. So basically, you guys think about, when we had truncated these values on Friday, it's always going to be this whole number and then the one above it. Right, so that gets us 18.49. And over here, we have 12.05. So 12.05 lies between 12 and 13. So we get 12.49. And I hope you guys are starting to kind of realize that all of these are about always at the 0.5 mark. They're not exactly, but they're close to the 0.5 mark. So if you're getting something really strange, then you should know something is up. Alright, here we've got 5.58, so that would lie between 5 and 6. And lastly, we have 25.53, which lies between 25 and 26. Alright, so from here, we always use these as a comparison. So when you guys are doing this, you're using it as a comparison, geometric mean with your quota. Alright, so between 58.79 and 58.5, you guys are comparing these values. So 58.79 is greater than 58.5. So if your initial quota is greater than the geometric mean, then this value, your initial, will go up. So this will go up to 59. Okay, use a different color here. Alright, so over here we have 18.06. We are comparing this to 18.49. 1806 is less than 18.49. So therefore we round down. So we would be rounding this down to 18. Okay, then we have 12.05. We are comparing that to 12.49. 12.05 is less than 12.49. So this value will round down. Okay, next we have 5.58 and 5.48. So 5.58 is greater than. So if we compare those, then this value rounds up. So this will go up to 6. And last one here, 25.53 and 25.50. Well, 25.53 is greater than, so this will round up to 26. Okay, so if we were to add these values together, this is 121 again, which means we have to subtract 1. All right, now remember guys, the whole reason we're adding these up is because, you know, if you add these up and this was 120, then you're done with the problem. You guys could cross out the adjusted ratio, and that would be your final. So it'd save you a ton of work, so always have to add these up. Plus you don't know how many seats you're actually taking or giving away. Alright, so adjusted ratio, we always take over here, so class size divided by, in this case we need to take away a seat, so that would be dividing by 59 and the one below it, 58. So we're going to take 59 times 58, and we are going to take the square root of that value, so class size divided by initial times initial minus 1, and again minus 1 because we need to subtract a seat here. Alright, the next one, we've got class size 745, and we will be dividing it by the square root. I'm going to use 18 and the one below it, so 18 and 17. Oh, that should be 17. Okay. Alright, so if you guys find that value, it's 42.59. Okay, and next we have 497 divided by square root of 12 times 11. Okay, so that's 43.26. And then we've got 230 divided by square root of 6 times 5. So 41.99. And for the last one here, we have 1053, and we are dividing it by 26 times 25. Alright, so remember adjusted ratio always works the exact same way. So we come up here, and 41.25 is the ideal ratio. So 41.25. Okay, this last one is the one that is closest to 41.25. So this one will lose the seat from 26 to 25, and then everybody else will stay the same. Alright, so again guys, if you are having troubles with some of this, normally it's a geometric mean. If you're having trouble finding these values, you know, you can try and come in and get some help. You can always come see me before school, otherwise we'll start doing the review tomorrow during class.